Welcome to today's Explainer. I am absolutely pumped to take you on this journey today. We are going to unlock the black box of literally the single most fundamental building block in modern electronics, the transistor. Specifically, we're going to demystify how these microscopic marvels actually work step by step. So if you've ever wondered how the device you're watching this on right now actually processes information, well, you're in exactly the right place.
To really appreciate where we're at today, we kind of have to look back. Picture this, it's 1971, and Intel just released the 4004 microprocessor. It was a totally revolutionary piece of technology for its time, and it contained exactly 2,300 transistors. For the early 70s, packing a couple thousand of these tiny switches onto a single chip, that was an absolute triumph of human engineering.
Now, what's really interesting about this slide is the sheer unimaginable leap we've taken since then. In just about 40 years, we jumped from 2,300 to over 2 billion transistors on a single modern microprocessor. Just think about that scale for a second. Thousands to billions. It's a phenomenal, explosive rate of progress, and honestly, it's completely unmatched by any other technology ever developed by human beings. Okay, let's dive into this. To understand how this staggering technology actually works, we're going to take a top-down journey. We'll look at the incredible scale of Moore's Law, ask why we even need these devices to act as amplifiers, build a simple semiconductor capacitor model, translate that into the real-world anatomy of a MOSFET, and finally, look at how we actually control the electrical current flowing through the whole shebang.
So, Section 1. The scale of Moore's Law. Let's start with the observation that predicted this entire technological revolution.
We're going back to the 1960s. Gordon Moore, one of the founders of Intel, looked at a handful of early data points and noticed a fascinating trend. He saw that the number of transistors we could fit onto an integrated circuit was doubling roughly every 18 months. He basically suggested this might just continue unstoppably. And wow, was he right. This explosive growth became known as Moore's Law. And amazingly, this trend has dictated the blistering pace of modern electronics ever since.
But it's not just about cramming billions of devices onto a chip. When these chips are manufactured, they're built on a massive, flat wafer. You can have a microprocessor on one edge and an RF chip on the complete opposite edge, maybe 30 centimeters apart. And here's the really astonishing engineering feat. Those millions of microscopic transistors have to maintain the exact same identical device characteristics regardless of where they sit on that massive wafer. Achieving this extreme uniformity, that's the result of decades of relentless progress.
Section 2. Why we need amplifiers. That brings up a great fundamental question. Why do we even need these chips to do what they do? Well, to make electronics useful, we have to process signals from the real world, right? Think about the sound from a microphone or the light hitting an imager in a camera. These real-world sensors generate very, very small electrical voltages. To do anything useful with those tiny signals, we desperately need to build an amplifier to make them larger.
So how exactly do we build an amplifier? We basically just need to go shopping for a voltage-dependent current source. If we take a simple circuit and apply some basic Ohm's law and Kirchhoff's current law, and hey, don't worry about getting bogged down in the deep math here, we can route that current through a resistor to get our output voltage. The math shows us that our output voltage ends up being proportional to our input voltage multiplied by a factor of K and the load resistor. Now you might notice a negative sign in the equation. That just means our amplified signal is flipped 180 degrees. But the key takeaway here is that the signal is multiplied. We've amplified it.
So our ultimate goal, essentially the core thesis of this entire explainer, is that to make modern electronics work, we urgently need a physical device that acts like a digital water valve. We want a device where an input voltage, kind of acting like a hand on a dial, can directly control the output current flowing through the pipe. And as we're about to see, a MOS device can do exactly that. Let's move to and see how this builds, starting with Section 3, the semiconductor capacitor model. Before we jump into the complexity of a transistor, we're just going to look at a basic capacitor, but we're going to build it a little differently. We'll use a top conductive plate, an insulator in the middle, and for the bottom plate, we'll use a piece of P-type semiconductor material. Now watch what happens as we progressively apply voltages to this structure. First, we apply a positive voltage to that top plate. Because the bottom piece is a P-type semiconductor, that positive top plate pushes or repels the positively charged holes away from the surface, leaving behind exposed negative ions.
As we crank that voltage up further, we hit this brilliant aha moment. We actually start attracting free mobile electrons right up to that surface. We've essentially formed a conductive channel of electrons. Now if we apply a second voltage across the sides of that channel, those electrons will start moving and a current flows.
Now, think about the cause and effect here. We want to maximize the density of those electrons in our channel because, well, more electrons mean much better conduction. So how do we do that? By shrinking the gap between the plates. If the thickness of our insulator decreases, the capacitance increases. And if capacitance increases for a given voltage, the electron density in our channel shoots way up. Basically, minimizing that gap maximizes the total charge we can control with our input voltage.
Section 4. Anatomy of a MOSFET. That capacitor model is fantastic in theory, but to build billions of these on that massive flat wafer we talked about earlier, we run into a physical roadblock. We can't actually access the sides of the devices when they're buried in a flat wafer. We can only make electrical contacts from the very top. So engineers had to ingeniously stretch and fold those side contacts up to the surface, and that modification is what creates the real, physical device we use today.
And that device is the MOSFET. It stands for Metal Oxide Semiconductor Field Effect Transistor. Let's quickly break that acronym down directly from its physical materials. The top conductive plate, the metal, is actually often made of a really good conductor called polysilicon today. The oxide is the incredibly thin silicon dioxide insulator sitting right below it, and the semiconductor is that P-type substrate we built our channel on.
Because we had to stretch everything up to the top, the modern MOSFET ends up having 4 distinct terminals extending out. We have the gate, which is that top plate. We have the source and the drain, which are made of heavily doped N-type material so we can make solid wire connections to the top of the wafer. And finally, we have a connection to the substrate, or body, at the bottom. Now, I know if you're used to simple 2-terminal diodes, jumping to a 4-terminal device might look a bit intimidating, but please don't let it scare you. It's actually highly logical. One of the absolute most beautiful things about the MOS structure is that it's perfectly symmetric. If you look closely, the source and the drain are physically indistinguishable from one another. This is a crucial difference from older bipolar transistors, which were super asymmetric. This symmetry turns out to be a massive advantage for modern circuit design, giving engineers just incredible flexibility. Remember a minute ago how we said we needed to make that insulator as thin as possible to increase our control over the electrons? Well, check out this mind-blowing scale. In modern devices, the oxide thickness has been reduced to roughly 15 to 18 angstroms. An angstrom is 10 to the negative 10 meters. To put that into perspective, that is literally just a handful of atoms thick. It is unimaginably thin, but it absolutely has to be this thin to maintain an incredibly strong, tight voltage control over the conductive channel beneath it. Section 5. Controlling the current. Okay, we've built the physical structure. Now let's observe what actually happens when we start tweaking the voltages on these different terminals. How do we actually control the current flowing from the drain to the source? It all starts with the gate voltage. If the gate voltage is at 0, there are no free electrons. No channel exists, and absolutely no current can flow between the source and the drain. The device is fundamentally off. We have to push that gate voltage up until it hits what we call the threshold voltage, which is often around 0.3 volts in modern technology. The threshold voltage is the exact point where we finally attract enough free electrons to form that conductive channel. Below this point, nothing. Above it, we have conduction. And this brilliantly illustrates how the device reacts depending on which valve you turn. If we keep the pressure, the drain voltage, constant, and slowly lift our gate, we see zero flow until we hit that threshold voltage. Once we pass it, boom, the current suddenly starts shooting up because we are creating the channel. Conversely, if we keep the gate voltage constantly high, meaning the channel already exists, and we turn up the drain voltage, the current rises immediately. There's no threshold to wait for because the electrons are already there, ready to move.
So the crucial point is this. Once that channel is formed, by tweaking the gate voltage up and down, we are directly altering the density of electrons in that channel. More electrons mean less resistance, fewer electrons mean more resistance. As our source beautifully puts it, the MOSFET acts as a variable resistor, specifically a voltage-controlled resistor. A voltage on the gate precisely dictates the current flowing through the device. We've achieved our ultimate goal.
Which leaves us with a truly staggering thought to wrap up this explainer. We've just mapped out the incredible intricacies of a single MOSFET. It's a symmetric, 4-terminal, voltage-controlled resistor operating basically at the atomic scale. But if this is how just one works, how on earth do engineers get 2 billion of them to communicate flawlessly, without a single error across a perfectly uniform 30-centimeter wafer? The sheer complexity of full-circuit integration is a whole new puzzle, and I really hope this foundation leaves you eager to explore exactly how those billions of switches wire together to power our modern world. Thanks so much for learning with me today.